Okay, we are recording, and this is Gerald King with Sampson Community College, and this is our ELC 215 electrical maintenance class for automation systems. And this is Tuesday, February the 9th, and I'm going to get our materials queued up here, so just bear with us, whoever's watching out there. It'll take a few minutes to get things queued up where you can see it from your computer. Put the full day in already. We're about ready to go home and go to bed. So, yeah, back tonight. Ready. So somebody didn't show up. What you guys do to keep it going. I'm glad that I had a good steady pace here for 20 years, in that one place. So let's see here. Let's see. Yeah, we only had a little bit of, just very little left on state. Well, a little bit left on station 3. So let's go here. So it was, let's see, 2. So, that's not. 155 for year. Okay. So this was the station 3 for the press. And we did go through and run it. We went through the graph set. How's everybody doing, by the way? Good and tired? Yep. Yep. I can relate to it. Hey, Thomas, how you doing, man? How y'all doing? Yo, come on in. Yeah. If you can, hopefully you should be able to see beyond these trainers. I'm teaching a Butterball PLC class on Monday, Wednesday, Friday, and that's what they're in there for. See, you should be able to work, be able to see above it, They'll be back in here in the morning at 8:30 on them things, and that's why I got them out, instead of packing them up every day. Yeah. They've been gone a while. They all of a sudden they come back, so. Okay. So I think where we left off, we ran it. We looked at the graph set, and we followed the program flow, how it went all the way through. And the next step would be they want you to explain how the safety relay is connected and what is its function in the system. So I'm going to pull up the schematic, and we'll just kind of do a little review on that. So you need your electrical schematic for station 3. I appreciate y'all coming. I know it's a sacrifice to do it. It really is. But hopefully you'll be able to use this on your job at some point. And it'll help you. It'll help you. But between this class with these international European prints and the motor control with the standard US print, between these two classes, it's preparing you for whatever kind of machines you get around. There ain't two kinds of schematics. You've got the US needles, you've got the international like this is, and that's it. So if you get a machine that comes from China, it's going to be drawn like this, or from Europe, or South America, or Canada, it's going to be drawn like that everywhere but the US. The US, you got the needle schematics like we use in motor control. You got the standard US schematics. So like those two systems, you're learning both of them within these two classes, and so it'll set you up good to be able to read schematics wherever you go, using a meter, and then pretty soon getting very good with a laptop, searching out these programs. You'll get real comfortable with a laptop, searching ladder logic programs. It's on another whole level than what you've been doing in the ELC 128 class. Okay, so this is a schematic for, and let me make sure that I've got it synced here with whoever may be watching, because I'm recording now. Okay, so I know I got it synced out there for whoever may be watching remote. And so the question on our lab sheet is, briefly explain how the connection of the safety relay is carried out and what is its function in the system. So we'll flip back to our schematic. And so the safety relay is over here. Now I'm just going to zoom in to this left section over here. And let's go, better back out a little bit like that. Let's go. Now the connections on the safety relay, and by the way, I can give you a data sheet on the, well, let's just do a little overview first of the things that are hooked up to it. This is the actual relay itself. That's the relay itself. These are the two contacts this in. Both of these are inside of one sensor. One sensor has like a redundant, normally open contacts, two of them that operate at the same time. On safety devices, they'll have redundancy in there just in case if one fails, and then it's not going to let the system work. They double up. They double up on planes. They double up on aircraft. They stay on aircraft. Their control systems, they've got a complete redundant system on airplanes. If something fails on one control system, it switches over to a redundant backup system. They do redundancy in a plant down in Rayford I've heard of, where they got more than one control on a mixing process. They got more than one PLC in the system. They got, so redundancy is used on safety things sometimes to make good sure that if a critical thing fails, or something else is there. But in this case, they've got two contacts to where they both have to close and both have to open at the right time. You got to have two things open. This is something to say. This could have been doubly hard for somebody to jump that tree. You got to see both of them close and both of them open at the right time. Or else this relay is not going to function and not turn on the contactor. So
how can you jump both of them? How can you jump both of them?
You'd have to put, well, the problem with that would be you'd have to jump them and then unjump them. You'd have to make contact with both of them from T1 to IM1 and then T2 out to IN, so you got to make them both at the right time and then unmake them at the right time. And that'd be super hard to, somebody had to manually do that, It'd be hard to do. So they got two things they have to make and break at the right time with the press. So if you will, take a second and just keep in mind here that both of them contacts there, both of them are inside of 1 minute. Let me give you a data sheet. I have that sent. So this is a magnetic sensor. It's got two more at a time. Switch, side yard switch.
Need one of those.
Okay, so on the screen here, I've got the Siemens SiGuard switching element. It has two ENC normally closed molded plastic housing. And let's just go through there. That's that long sensing element just at the bottom of that clear plexiglass guard. When that guard comes down, there's a magnet. You want to take a second and step over here if you don't mind, and take a look at the front of this. You can see what kind of I know everybody's blood circulation. This is sensing unit to have two. It's got two contacts going in right here. This is a magnet, and that magnet, when it comes down, it energizes those contacts. It makes that's the physical magnet part. It's going to take a look right here. And just here, you get light red, you got to need to do it one time. Come right here. This is the magnetic sensor got the double contact. This critical. This here runs the safety to it. That's the safety. So I'm going to give you that. That's the actual relay right here. They're getting real popular. Safety relays are big time in the plant, in the hot plant where you're at. Nathan Batson showed me some panels in there where you got a bunch of safety relays on that. You move your big stuff that does all the sheet metal cleaners now.
Oh, you're talking about over there, New Road?
No, here, Fire Bridge Road.
Oh, the Fire Bridge?
When they make the hot leaders.
I know you're talking about that back.
Yeah, Offset's got some new equipment that they take sheet metal in. It automatically makes a hog feeder. It thins and punches metal and stuff.
Yeah.
And they got a bunch of safety relays in that machine. So anyway, the data sheet, it tells you about what it is, a magnetic operated switch. It's giving you the distance, switch distance, secure switching distance off if 15 millimeters away, if you get a magnet 15 millimeters from it, then it shuts off. The safe, secure switching distance on will be 5 millimeters. So when you set up your gap between the magnet and the sensor, that's a very important point there. You know what I mean? As far as the distance. So whenever they set it up here, the position of that bar right there, this one, or the stroke, I'd rather I say the stroke, how close it is to it. It has to be, you know, within a certain number of millimeters, critical safety to be alive. That's what we're getting at. You don't want to touch it. If it hits it, it's going to be just going to scrape it. You know what I mean? You want to get close, put in, say, 5 millimeters, and then you get it. It doesn't touch. So it's just here. See right here, this gap in there? You see a gap in there. Sensors like that, they're magnetic and they don't really physically touch the magnet, but it's close to it. It's like on the door, there's many of their security systems on. And you have the door closes, there's a little magnet on the door, and it's near the pickup. It closes quick, it doesn't touch, the magnet doesn't touch it, it's close to it. So when you have a gap, when you have this, it has to be a certain distance. Or it's just not going to be a reliable contact. So that's one thing to keep in mind with these sensors. And then here, the number of normally closed contacts for auxiliary contact, there's 2. And they consider it normally closed. Now, they're closed when it's down, which is their consideration for a normal position would be to guard down. That's what they're calling it. I thought they would have called it normally open without the magnet there. And then when you energize, it would close. They say normally closed. Down position is closed, you know, with the magnet in front of it. And that's pretty much it. There's other stuff that just not major for us, but anyway, that gives you you know, data on that and the part number so on. Okay, let's see. Here. I'm having to resync. Each time I change the screen, if I don't resync it, whoever's out there doesn't see it. Yeah, like I had to go back and do a re-trigger the screen share, and then people out there see it. So whoever may be watching, that's the sensor that's got the 2 normally closed contacts. It's a chore trying to remember to do this. If I'm teaching people the way everybody's remote, I don't have any trouble remembering to do this. But when I got a group here and somebody out there, it's hard to remember. It's hard to remember. Okay, so then we flip back to the schematic itself. So again, that's what those contacts are that feed here. And you got a power internal signal at T1 that goes out through that contact, and it comes back to input 1. So it goes out and comes back, and then another one leaves out of this T2 terminal, goes through that other contact and comes back in input 1. So it's looking for 2 inputs to make and break at the right time.
Let's just say T4 and IN goes out.
Mm-hmm.
Right? If you only move the T3 to IN3, think it still works?
I don't know. I don't really know if you could do that, because look, they've got separate send and receive inputs there. And I don't know if internally the T's are different, if they're unique. I don't know. I'd have to do some digging into that. I don't know.
Because like, you can switch it if it goes bad.
Yeah. 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 We'd have to sort of dig into that. I don't really know, to tell you the truth. The best thing is to have one in stock and don't modify anything is the best thing. The see for input 3 and input 4, they got separate signals that go out, and they jumper them because they're not using those. So that the whole relay has to be satisfied, but all 4 inputs have to be made for that relay to work. You got to have input 1, 2, 3, and 4 for this output to turn that contactor on for KM2 coil to energize. And so when it does, when all 4 inputs are on, you get output here on terminal 14. It turns on that coil for KM2, which is a contactor like so when it energizes that coil, let's go back over to the other side of the page and you search for that cross reference number, the KM2, and it goes over. And these 3 contacts are controlled by the coil we just looked at. So that coil magnetizes, and it makes all 3 of these contacts close, and it lets your variable frequency drive make a connection over to the pump motor. And so even if the variable speed drive, even if it gets a run command from the PLC here, if the PLC tells it to run and it runs, it ramps up, unless the KM2 gate is closed, then the pump motor never comes on, which means that plexiglass has got to be down. Now you kind of might want to wonder why would they be doing this outside the PLC? And I've read that safety functions like this with safety relays, they'll have a high reliability safety relay apart from the PLC, just in case if something fails with the PLC system. You got an external control that's a high reliability relay that may be even more reliable than the PLC itself. I mean, they say that they're high reliability. They'll have that outside the PLC doing a safety function just in case if it was to hang up and stay on, if that makes sense. So you've got an independent control here with monitoring here that the safety gate's down, and then that contact with the relay turning that contactor on, and then that's like a permission, like a drawbridge that gives permission for your variable speed drive to connect with the motor. Even if the PLC is saying run, this comes from the PLC output. If it says run, it goes into acceleration, it'll accelerate the drive. But even if it does, it's not gonna, the pump's not coming on unless that guard's down. Okay, so it's an independent thing from the PLC. That's, some people prefer to do their safety functions independent from the PLC, which is not a bad idea because they do fail sometimes. Outputs can stick on a PLC and just stay on. They can just click and stay on. They can weld shut, you know. And so it's a definite possibility that it could happen that way. So all you have to do to describe your connection for the safety relay will be this in your own words. You can say that the safety relay, it monitors 2 magnetic contacts that tell you if the guard is down, if the press guard is down, and then the safety relay in turn, it turns on a contactor that bridges the connection between the VFD drive and the pump motor. Okay. Now I'm gonna let you kind of tell me from what you see here. What do you see? Tell me about these. Yeah, and what closes? You see that the plexiglass guard, it's got a magnet on it, and so when the magnet comes down with the glass with the guard, the magnet triggers these, which says that the guard is down. So when they both close, then the relay then turns the contactor on. The contactor is the one that allows the VFD to connect with the pump motor for the press. Uh-huh. It monitors the guard, but you want to put down, yes, before it lets it turn on the pump, before it lets the VFD control the pump. I'd be specific and say, it monitors the guard being down with magnetic switches. Double check this. I don't know what it is. Hello? This is I'm 57. I'm not 63. I'm going to be 57. Okay, let's see here. Let's see. Now, that's probably enough of explanation, isn't it? I think everybody knows. Put in your own words. And while you're doing that, I'll give you a data sheet for the actual relay itself. Uh-huh. Yeah. Uh-huh. Yeah. We can look that up. That might be one of it. We can look it up. I've got a data sheet. We can look that up. Let's see. What I'm getting now, it's probably got that in there. I don't have all the what it all is. You might find it before I get to it. I mean, this information on that product line to come out of. Yeah. Yeah, I believe in having information. It's because you can't memorize all. You can't remember all this stuff. The main thing is kind of having stuff organized in most books, and then when I start building the system, then you can follow what you're going to say. You have to get those. All right, that's a data sheet on the relay itself. That's at the end of, it should be at the end of missing. So you didn't get a front back? Okay. Well, I ran copies one time, you didn't have front back, and that's the back we know. Yes, we are. I think I figured out some of it.
These two should be front back.
I went back and rewound, I saw them. Just fold those right in there. This is good. You'll have it. Because sometimes that confidence that the paper is sticking to is weird. I don't think that strange how that happens. Either it's supposed to be, you just get it back and not, you got something. The confidence over there is. It's hard to sit there and put it in the things you're going to put, I don't want to do it, it's something to do. You can't always. Sometimes you run out of time and you find out like now. Did everybody get a front back on the get the front back on this? Yes, the volunteer. Get front back on this. Now, so one of your troubleshooting points is going to be this: the LEDs that are here. When we start running it, you stand in front of it and you notice when are the LEDs on and when are they off. Which one stays on, which one goes off on and off. Okay. So for an output, you should see it go off and on. For device, it should stay on. That's my memory. And so those, again, those are little small details you'd look at. If something's not working right, you're going to be looking for LED indicators to tell you the status of that module. Like on the PLC, LEDs are the fastest way to troubleshoot the system. It's your first thing to look at instead of grabbing a laptop or a voltmeter. Look at your LEDs first. And you're going to use a voltmeter a lot, and you use a laptop a lot, but these are very important. The lights are.
That FS could be fail-safe. So you got fail-safe up there, and you got the FS down here.
That's probably that's probably what it is. Fail safe, yeah. Fail safe, yeah. That's what it would be. Fail safe is a term. It's a term that's used on critical control circuits. It's a term that's used that they create them, that they have a fail safe feature in them. It's a backup in case something fails. Yeah. Mm-hmm. It has some type of backup to it. That hey, come on in and get you a seat or. Okay. Make sure I've got that.
Yeah, I'm just saying, this year, not saying, or any of that. And I think most of the law, they don't know the law.
How you doing? Good.
Yeah, yeah. I would be a good way to look at it.
Okay, and then,
I'll start calling Tom for that movie.
boo boo,
That's where you'll be better.
he's asking you where what is,
Just start asking where you'll be better at.
Yogi Bear. Yeah. All right, that shows the product line for that type of, for safety relays, different models. Different models, and then it shows,
So the emergency
I
stop
think,
is actually the same thing?
you can use an emergency stop with this,
Oh, okay.
and then you've got an independent e-stop circuit that's separate from PLC.
I seen the e-stop.
Mhm. Yeah. You could use the e-stop with this instead of using the e-stop with an MCR relay, like a master control relay. Normally, you'd have an e-stop going to a contactor that's used as an MCR relay, and that will be independent. If you hit the e-stop, it would knock out your big MCR relay, and then that would actually kill power to the PLC. You've always got to have something outside the PLC that can actually be the watchdog over the PLC that can knock it out. You know, if you don't have it, you're messing up because outputs stick. They stick sometimes on PLCs and then something to stay on when they ain't telling you. When the processor's not telling that RAM to come down, sometimes that output is sticking, that RAM comes down. That press to come down when the processor not even telling it to come down because the physical output sticks. So you got to have something on the outside, independent, that can knock out the control power for the whole PLC. You know, you need to have that. So here they've got an e-stop wiring in. Instead of them having the magnetic sensors like on this guard, they got a physical e-stop that they're using it for. So safety relays they can have different devices in there for a contact other than a magnetic switch. It can be a physical e-stop, you know. It looks like they got a double contact there on that e-stop there, like with two contact blocks. They have two. You know, if you zoom in, they do. Like what we're doing here with magnetic sensors, they got an e-stop, and on the back of that button, you got a double contact block, and it's actually telling the safety relay go or no go. You know. And then here, this is something else. This is not on our system. They got two switches in series, and then another one here. So for the fail-safe input, they've got three things in series on that setup that have to be made for your fail-safe input to be on. See that? Then they've got input 3, just jumper. Now, that's not on this system. It's just an example that Siemens is showing how these things can be, how they can be used, and how some people do use them. So it's good to kind of look at different things to realize that depending on where you work at, they could use that relay. The relay could be controlled by a manual contact versus something automatic like it is here.
So you can't go in a relay anyway. You can't go in that relay and change anything anyway, can you?
No, you really can't
You
do
gotta
that.
buy
No.
for what you need. Ain't it pre-wired already in there?
You mean internal?
Yeah.
Yeah, there's a circuit board, you know, you can't change anything inside of it, no.
Oh.
No, you can't do that. Nope. Okay, so anyhow, that just, you know, you would explain, you know, how that relay is connected, in your own words. And then we move on. Yeah, McGill, it was the question in the, on station 3, do you have that station 3, lab sheet? You do? Okay. That number 7 there is wanting you to explain how that safety relay is hooked up. Just kind of briefly put what it does, how it's hooked up, and what it does. And then we're going to skip number 8. It talks about modifying, and not modifying anything. Skip 8.2. And what they're talking about is this. They're talking about getting rid of the safety relay and letting the PLC do it. And we're not going to do that, but they're just, this material includes modifying, and I don't think we need to get into that. A proposed change for management method of the safety relay, instead of directly activating the KM2 contactor, the safety relay will activate a PLC input, which by programming will activate a digital output that will turn on KM2. So they're actually talking about putting PLC as a middleman in there, and it could be done, but I would not do it. Then if the PLC fails, you're still messed up. You don't have a safety relay. No. You know what I mean? The reason for having a safety relay normally is to have something safety outside the PLC that has power over it. You know what I mean? That has power outside of it that can interrupt the PLC's actions. Like accountability type thing. You know what I mean? It's like somebody that can override what you say, that their supervisor or whatever, and just in case someone makes the wrong decision. So SMC and their materials, in each one of these, they have recommended modifications of how would you do it. We ain't got time for that. We just ain't got time for that. The last question would be this: what's the function of the frequency converter or the VFD? What's the function of it, and what other function does it fulfill? So there's two functions that the frequency converter or VFD does. And I can, just as a refresher, it does, exactly. Look, what Thomas said was your variable frequency driver VFD, it converts single phase 120 to 3-phase. It can go up as high as 230 on that drive, 3-phase. So that's a special VFD. It's a power flex. When you get a special order, we'll get you rid of it, where they'll take single phase 120 coming in, and then they'll boost it up to say 230, 3-phase. That's it. It's a single phase and 3-phase out. So in this case, that's what that is. That is a special order. That's one feature that it does. The other feature is it allows that pump to run at different speeds. It has an adjustable speed pot on the front of the drive. It lets you change the frequency output of the drive from something 60 hertz or below. It can go 60 or 50 or 30 hertz and make the pump run slower. So when you look on the front of the drive, you've got a manual knob you can change that speed with, a speed pot. So that's your two functions. It gives you a variable speed pump, and then it gives you the single phase to 3-phase converter. They make this educational system simple power-wise. It plugs right out of that bottle of it. They're rated 15 amp circuit, rated 120 circuit. The whole thing, most of the energy is doing stuff on here is actually in that. Solenoid, the 24-volt solenoid, but most of the action stuff is actually air. there's not a lot of electricity being used here. You know, you got one hydraulic station and the rest of it there. PLC control area. So it's, it don't require a lot of big circuits, you know, power wise to run this. Like in food processing and pharmaceutical, the air stuff is clean. That's what they'll use. You go, like where you're at, you talk about air stuff, a lot of pneumatics. Make boxes automatic. Yeah. I can picture that, you know. Yeah. Okay, so that answers that question. I think that wraps up station 3 as far as that sheet there.
But, no. We did that on the first.
It does. So now I'm going to give you the pneumatic and the hydraulic drawing for that station. We're going to take a look at the schematic of the valves and the piping. Okay, we'll take a look at that briefly. So that's important. You need that. It needs to be something that's just in your. Included in your customer. I bet you went in about 5 o'clock, 6 o'clock. 5 o'clock.
Was it still with this station?
Yeah, this is the last thing you get. This shows your valve, your pipe and your cylinder, and your hydraulic. Station 3.
Maybe we did. I guess I'm thinking
Station 2, yeah.
it looks almost
It looks similar, but this has got the hydraulics, which is something that we have to look at. We're gonna look at the hydraulics now. None of those stations have that. That diagram a little bit, we'll move on forward. Okay, so for your pneumatic and hydraulic, now let me resync my Zoom here, because I bet it ain't synced. Let's see.
getting tired, but I didn't think you were gonna lay down on
Mm-hmm. Share. all these screens I got in the background, if I don't go out there and that is when I do a screen share, if I don't point to the screen I want to share, the person, whoever's watching through Zoom, they won't see that screen. You know, I can keep switching screens, but if I don't resync them, it's touchy, you know, it's a touchy thing. I just want to make sure that because there's nobody out there, nobody's logged in right now watching. They'll watch after it's recorded, you know. I guess somebody will.
I'll go back and sometimes.
Yeah, yeah. Yeah, I see later on that you are, and there's a few that do watch them. Yeah. Mm-hmm. It's good if you got time. It's good to go review them. It is. But this is for station 3 here. Now on the pneumatic end of it, there's nothing really majorly new. I'll show the rotary actuator. The rest of it is like another repeat there. So on station 3, that arm that goes out like this right here, that does a 180 like this, it goes out and it'll get the block, bring it over and put it in the machine. Then it's got a mid position. It's got 3 positions for that arm, that rotary arm. This is the symbol, a pneumatic symbol for a rotary actuator. It's got an arch in it, and it has 2 air lines that come from a 3-position solenoid valve. We've got 2. It's a double solenoid, 3-position valve with closed center position, and the coils are controlled by the PLC. And basically, what you got here is when you energize one of the coils, that arm will move. You know, it'll move from home to forward or either back to home. And if you energize this one, it moves the arm the other way. Now, the way it stops it in mid position is that when the PLC, say when it turns on that coil and the arm begins to move, when it gets to the point to where this sensor, this is the 3 magnetic sensors, the A0 sensor, the A1, and the A2, those are the magnetic sensors on the back of that unit that light up as it moves through its stroke, you know, the 180 that it does. So as it moves, when the PLC sees this sensor turn on and you get an input for this sensor, then the PLC shuts off the valve. It cuts off the electricity to the coil. And when it does, this spring and this spring forces the spool to the center on the valve. Now those flat lines mean that it's a closed center valve. It means all 5 ports are blocked. When you cut both of the coils off of that solenoid, both ends are de-energized, the spool centers it goes to the center with those springs, all the ports lock up, and therefore the arm locks up. The arm locks up wherever the sensor is. Because the sensor tells the PLC, cut off the coil, cut off the solenoid. Because it's where you want to be at from mid position. That makes sense? So there's no hard stop there. There's nothing physically there that stops it as far as like a mechanical stop. The PLC reads this. It tells it to begin its stroking. When it sees this input, it just shuts the coil off. Whichever coil it's on, it shuts it off, and it locks up the ports. It locks up the air coming in. That's your air pressure coming in, and there goes your ports going to the cylinder. It just locks everything up, so it just sits, and it doesn't drift. It doesn't drift because the valve ports are sealed, and so the arm doesn't drift. It's solid where it is. It gives you a 3rd position, you know, by doing that. So that valve has to be a closed center type valve. If you replace it, it can't be an open center. They make valves with open center. They make tandem center. They make floating center valves, and then they make closed center valves. So there's about 4 kinds of valves that you could put on that valve bank with different center conditions. And you got to be careful what you put in there, that it's the exact same, that the symbol here is the same in the center, meaning a closed center type valve. When it's in neutral, that all the ports are blocked. And then you have a speed control. You have an adjustable flow control here and a flow control here that controls the speed of that arm, whether it's going away from home or back home, going forward or back. So you have speed controls, small needle valves. Those are adjustable valves that are mounted on the cylinder itself. The rest of the stuff is like you've seen on other stations. The vacuum cups, they get vacuum from. There's a regular air valve that shoots air into a vacuum ejector or vacuum generator, and air shoots in out an exhaust, and when it does, it creates a pull on them cups. So when you send air straight through something, if you have an exhaust port on it, then that side port does a pull. It gives you a pull, And so that's an inexpensive way. It's called a vacuum generator, and you run air through it, and then it makes these cups have a suction to them. This is a sensor that verifies you have a vacuum pull, and that sensor has a wire going to the PLC that tells the PLC that you have a vacuum pull on that block, that it's okay to go ahead and move that arm, So if the vacuum sensor's on, it knows you can go ahead and bring the block in, or take the block back out. So, the wiring's not shown here because this is a pneumatic diagram just showing your hoses and the valves. This is purely pneumatic diagram here. If you wanted to see the vacuum switch or the coils, that's the wiring for that. You would just simply go back to the electrical diagram, and you would look for V. V is the label for that sensor. You could go back to your electrical drawing for this same station, and you would just go to your input section on the PLC, and you would find where it has a vacuum sensor, which is right here, right there. Yeah. So they got a different symbol here this time for vacuum, and we'll look at it. And that's one thing that the guy that did these drawings, he didn't always use the same thing for vacuum. He's got two symbols he's using for vacuum sensor. So if we go in, there's a P in there, which means pressure. It's normally open. And so that's his choice this time for a vacuum sensor or pressure sensor instead of the one that we saw on a previous station. You got the 24 volts going in there to it, and then it goes to the PLC for vacuum input. So this is the sensor for vacuum, and it's input 7. And if you go back to your pneumatic drawing, this is the actual sensor right here. It says V. So you got in your hands, you have the electrical drawing. It shows electrically that the vacuum sensor goes to input 7 on the PLC. And then you've got the pneumatic drawing showing the hoses piping, which is this. This shows the physical hoses and the cups, and it shows the actual piping. And wherever you see an X at, the second output on that solenoid valve, they plugged it because the vacuum generator doesn't need two hoses like a cylinder would. So they plug it. That represents a plug. It'll be a piece of plastic that's just stuffed into that port to block that port. So if you see, whenever you have to come around, for those of you that are there, I can show you right here. I got my finger on it right now. This is where they actually plug it. I can actually do it with the webcam. We do that. I'll do a screen share stop. Let's see if I can do that without knocking the video off, maybe. But I love this camera. This thing is catching down. You can have sharp things. It's awesome. It's a nice camera. Yeah. I started trying to know if you find out like it, and all of a sudden Bonnie sent an email out. Does anybody want a document camera? We've got some document cameras. Somebody said they're really good. other man, that's got that photo frame right there. By the time you let go and give up on something, same thing falls like you learn last.
So the night that
Yes. Absolutely. Because you can focus that ring on there, you can see how that is, I think the focus all over, you go right back, look how sharp that is. And it takes you just a second to get it. But here I got my finger at, this is where they plug on the out first. Matter of fact, you go up there, you see where it says B plus, that's the solenoid valve or vacuum. And they're using the top port's plugged in the bottom, it says B plus. They're using the bottom one, they're not using the top port. See that? If I get this down in there, you see the B plus hose, that's the B plus hose. It goes to the vacuum generator, this is the port. The rest of them have like two hoses on there, like top and bottom. All the rest of them have two hoses, just puts no line. Each solenoid valve has two hoses, the top and the bottom. You know, each cylinder is set up. So it doesn't hurt anything, it's just for it. You can plug it if you have a cylinder, a single action cylinder, a cylinder, you plug it on one port, and all you need is one to go to a single action cylinder. You want to put it on the frame. So that's what the frame. You notice now all the valves are labeled, like big vacuum, and then the A plus that's this double solenoid valve here. When you see two mains on it, there's actually two coils in there, and there's actually two overrides there. Look how short that is. Man, that's a cat. The camera right before you couldn't read that. Could not read that.
No, we can read that.
And here you got an override, you can push this one, push that one, and it's the same thing, because you're going to override on that one, the A plus port or the A minus port on that back. The other one is single action, they got one override that you can push the wheel up, or you can push and turn and lock it, and it'll stay in time. If you just simply push it, it'll do a quick override and you release it. But anyway, that's I got one of these at home. I got a second one. Barney had an extra one. I got one. I ain't got to drag it back and forth from home. I got one I leave at home. I'm teaching Murphy on Monday night. I got a Zoom station at home. I have to bring the computer back for him, but I ain't got to do the camera that way. Okay. All right. So back to that. Now, the rest of it, as far as cylinders, is the same stuff that you've been seeing, a two-position, single solenoid with a spring return, that when the coil's on, you get this scenario. When the coil's turned off, the spring gives you this scenario as far as the airflow directions in the valve, through the valve. To make that cylinder go out or come home, there goes your sensors. Move on over. It's the same thing all the way across. Now you get to, now some of these have like a double rod for stability. When you're moving something like a plexiglass guard, you don't want, if you had a single rod cylinder, it may have a tendency of not being stable going up and down. A double rod is going to be rock solid all the way through the stroke, it'll be stable. So that's where they'll use a double rod for something like that. Now, the hydraulic press is our first time talking about hydraulics in here, and it's important because this is a area that you have to troubleshoot for sure. So let's enlarge. And let's do the overview first. This is actually the reservoir. This is the tank that holds the hydraulic fluid. This is the fluid here. This is the actual pump. This is the motor, the electric motor that's run by the VFD. VFD runs this. It's a unidirectional pump. This is a screen that's down in the hydraulic fluid that will, as it pulls it out, it's gonna clean contaminants that may be down in that reservoir. It's gonna come up through the pump, and you have it. You don't know what this is. Somebody said a flow control. It's not a flow control. Mm-mm. Who was in our pneumatic class today, this afternoon? We talked about this. A check valve, yes, sir. So it has a ball, and look, if you get hydraulic pressure pushing up against the ball this way, what happens to the ball? The ball will lift, and then the fluid will go around the ball, and it's going to go up. It's going to move. But let's say if you're pushing, and all of a sudden somebody cuts the pump off, can the fluid go back to the pump or not? It does it. When you shut it off, the fluid that tries to come backwards gets blocked here, so it doesn't let fluid come back. That's called a backflow preventer. It's kind of like at your house. Those of you that have city or county water, you got a water line out there at the road, and between the road and your house, there's a check valve down the ground, and so it lets you get water from them, but it doesn't let your water push back and contaminate the city system. Now, just in case if you have more pressure, it would. There's one of these in your yard if you got city or county water. You know. So anyway, so after it leaves here, you got a pressure gauge. It tells you what the pressure is from the pump on that line. This is a relief valve, a pressure relief valve that does this. This actually, however, it's set with an adjustment. This has spring adjustment, and it is set with a cracking pressure in here of some level that sets the maximum pressure of the press itself. So let's say, for instance, if you wanted to limit this pressure to 1,000 pounds, 1,000 psi on that press, then what you would do is you would dial this in until the maximum pressure, with it running, the maximum pressure would be 1,000 pounds on this. And you actually dial that adjustment where that spring is, you calibrate it so that this would give you no more than 1,000 pounds. And the best way to do it will be to do it when the ram is down, when it's actually got pressure on it, when the cylinder's energized and you see it pegged. It's to set it then. You could go in there and do an override and make the ram come down, and you can set your relief valve then, adjust it. So all of your hydraulic systems, most of them are going to have some type of a relief valve that's outside of the pump, unless it's got like a self-compensating type pump that's got something built in that does that. And so guess what happens here? So let's say if you set this to 1,000 psi limit, and then the pump has a capacity of running at, say, 2,000 pounds. So the 2,000 pound comes out here, and then what happens to this thing turns on. It cracks on, and it starts dumping back to the reservoir. So it dumps it just dumps right back round and round. Everything that's above 1,000 pounds, what it does. So whatever's above 1,000, it actually just dumps it right back to the tank, and it recirculates. Okay. So that's your return line, straight back to the tank. It never goes out to the machine. Then you go up the line, and you have a pressure input on the hydraulic solenoid valve. The hydraulic valve is located under the press. If you look behind there, there's a small hydraulic tank and a valve down in there. It's up under the chimney. And this is what we're talking about now. It's a 3-position hydraulic valve. So the pressure port from the hydraulic tank, it goes to the valve on the P port. But guess what happens? This center position, this type of a valve design is called tandem center. It's not a closed center. So if you have a valve that's called a tandem center, here's what it does. When you de-energize that coil and that electric coil right there, and neither one of them have voltage on it, this spring and this spring will equalize the spool to the center position. And then the pressure port from the hydraulic pump, it goes straight in and straight back out, back to the tank. And it actually will just recycle back out and go right back and dump through a return filter. It will clean that fluid again before it dumps it into the tank. So it's another filter, another strainer that will clean the fluid. It will dump it right back in there. So if you're not telling the pressure to go up or down, if you're not willing to press up or down, if it's just sitting out, then the pressure from the pump, it does a deadhead at the valve. It does a deadhead. It actually dumps back and just releases itself. It's like a self-relieving function. So picture right here that the pump will actually run right around through that port and right back to the tank and round and round and round. And it won't meet any load. It'll be unloaded. It unloads the pump, basically. It unloads the pump. So the pump actually relaxes. The pump relaxes. It doesn't meet a deadhead condition when it's not being asked to go up or down. You know what I mean? And they call that center position tandem. That right there, it's T-A-N-D-E-M. Those if you take a hydraulic class, that's the term that we're going to be getting into. It's a tandem center. Tandem center position. First is a closed center. A closed center is what you just looked at. A closed center is what you looked at on your arm. That the arm, it has a closed center, so when it gets to the center and you see that the section, then it goes to the center position, it's closed position, as you see. The hydraulics, a tandem center valve is a good choice because the pump doesn't strain, it doesn't overheat the pump. And another thing is it doesn't overwork the relief valve. The relief valve is not constantly diverting back. It just lets the pump go ahead and dump freely back to the tank. And it's not really overworking the relief valve either, so it's not going to overheat the relief valve. If that makes sense. Whenever you're working with this is the up and down ram, the cylinder that does the pressing of the bearing. It's turned vertical though, instead of sideways. When it's working, the relief valve is functioning off and on, limiting pressure. But when you're not going up or down with either one of them coils, then that pump gets just freely dumped with no load on it. So your A and B outputs is what goes up to the cylinder, but they go through some flow control valves. So the A output, instead of it going straight to the cylinder, it goes around here through a flow control with a bypass check that we've already discussed, the reason for having a bypass check. So it has two of those on there, one for the extension stroke of the press and one for the retraction, one for up and one for down. So the A port goes through flow control, speed control. It goes up here to the cap end of the cylinder. And then the B port of the hydraulic valve, it runs through another flow control and it goes up to the rod end. And that's it. It's very simple. The ram is positioned vertical. It has a retracted sensor of E0 and it has two extended sensors. And the reason for the two sensors is because of the two bearing types that you have here. You have two different thicknesses of bearings. So when the ram comes down, the ram can be at two different places because of that. So it picks it up no matter which one. I keep thinking there's something. I think it's that bigger right there. No bigger not here. Because these two, when they get in that press box valve, got 2 cents on the end of it. That makes sense. They do. They call it blue. That's why they got 2 cents. Each one of these two, depending on how far the text slopes down, then it's going to bottom back. I got 2 or 3 cents on that press and one on the other. All right. Okay, so that's the whole scoop of the hydraulics, and you know, everybody cool with that?
Sir.
Yep. So now we're ready to click. Yeah, there's a lot going on. There's a lot going on that page right there. But I'm trying to make it fair for you to have all of your system information there. So when we start our troubleshooting, that you'll be covered. You'll have everything in front of you. So let's see. So next would be will be station 4. Okay, so I'll give you some stuff on that. If y'all want to take a break, do you want to get a break in, or do you want me to? You want to take a break? Let's take us a break. Let's take us a break. Let's take a 10-minute break. I don't want to burn nobody out. I know it's 20 after 7. We'll start back at 7:30, and then we'll have us another 30 minutes or 25. You know, I know people. You've had a long day. Okay, so we're taking a 10-minute break. Whoever's out there watching, it's 7:20, and we'll start back at 7:30. So whoever may be watching this, I'm just looking at everybody's faces. That looks like people might be getting tired of listening for a little bit, you know. Mm-hmm. Mm-hmm. Yeah. Yeah, it's hard. It's tough. Yeah. Mm-hmm. We'll get everybody do some phone discussion of sentences over here now. We'll let everybody do something on everybody get the call. The next lab cost measured on the computer. Hang in there with us before we know that we have all these tabs and we might talk about it. Get problems. get your schematics, you can see the laptops out, and what how to use laptops with your program, without a lot of, without talking. Very cool. I'll give you everything to this station here tonight. And the Thursday night, we'll wrap it up with those two. So this week, you'll have everything in hand for the whole station. Next week, so Tuesday night, we'll plan on using our laptops. I want to learn how to connect it, Ethernet, put it on IP addresses, and choose which one you want to go online with it. You can choose the station, and then get there and go online and see the log program. You can see a lot of that. That point on that, we can use the computer, a laptop, sit up right now, and do what you create programs with. Some this time, you know, the troubleshooting systems all in there. It's got a lot of whole bunch of big programs. I'm gonna take the problem in there, one problem per station, and I didn't want to do too much. We have somebody like you, or somebody that do that, I would be you. However, I've got 12 people in the class, get everyone to do that, it's a big person. We would be able to have it, somebody can be on. That's right. That's it. I've got the Ethernet cable, got me on the line, we've got several, you put like three computers on that back row. You put two of them here, one of them here, I've got Ethernet here. I've got two here, and three right there. If you tie in, you tie into the switch, no matter where you are, get any of them, put it back. You can get all the laptops have some software on it, and got that all the same person. It doesn't matter what laptop it is, it doesn't matter what they do. You can see everything, no matter where you go. Like where you are, I guess some department that way, you can't do it together. I know that Russell keeps stuff going. So it's bad work. We'll get you up here today for a few minutes, check it. These two semesters here, again, measure them, we've got metal in front of the plastic. But this is a bad one, that is a bad one. We'll go there around. Very much up to your mirror, about how fine the holes on pretty. And you can check holes. That's the plan, with the 30 all diagrams and one of these Tuesday, laptops, and then early next week, we should start working. That's how much I've been on that list semester and both of those. Gave us a blueprint on that. Gave us a blueprint on that. Just all of that. No idea what it is. I'll share everything tonight, and we'll get high spots for this here. That's pretty good time. We'll make good progress on it. It takes time. But believe me, once you get everything in hand, your hands will be easy. Move it up, that's there. You can use laptops, so the thing you enjoy yourself once I get that home. I tell them Thursday night, we'll finish up this last two. I'm gonna give you everything before now. And let everybody come over and do some air and the ball things. Check with you all. See what we do, what we feel too. Where it picks up fast and then they check those sensors. And Thursday night, those two. And then Tuesday night, we get the laptops out. But you have to go look to have a lot of fun. And that Thursday night next week, I'll start that. We're timing out good. We're timing out good. If you look at the number of weeks that you have left, so I would say that once you, if we start, say, Thursday of next week, actually doing the bucket, once you got the laptop thing, you know how to use it, then we should be able to start the debug, let's see, Tuesday, Thursday, that Thursday of next week, starting that up, which would be the 18th. And then from that point, 1, 2, 3, 4, 5, 6, 7, 8. Let's see, where is the, okay, I don't have the last day programmed in here as far as the semester. Let's go back out to the website. Let's look up. Go back out to I didn't want calendar, I wanted the actual academic calendar for college. Hit calendar, then you go to academic calendar. It'll give you the dates of, this is our spring. So this is showing you the semester ends on April 16th. April 16th. All right, so with that being said, that we'd have about eight solid weeks of troubleshooting using the laptops and the whole thing, the debugging. You get about 2 months. You get about 2 months of debug, which is a lot. You get so much of it that you'll be satisfied. I mean, you'll say at the end of it, I think I know enough. I mean, seriously, you will. You'll say, I think I've had enough, you know. It feels like it takes a long time to get there, but believe me, you will have had fun when it's over with. Yes, if it ends on the 16th, which will be a Friday, I think I counted 8 weeks. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, you get you get a little over 8 weeks of actual debugging with all the information in your hands with the laptop and the schematics and the meter. You get 8 weeks and 1 night with everything, which is actually pretty good. Okay, so we're going to flip over and I'll give you your information for session 4 now. What we'll do, we go ahead and cut the stations on, let them be warming up. I'm gonna use some water. We'll cut the stations on, and that way when we're gonna go right to place or something, start using the meters just to check real quick. You can have Sam on the line. I don't before you, but you wouldn't be talking all the time, and you're not doing anything, because, you know, not there. Grab you some gloves and pass them around. The gloves, they're coming around the other way. I'm gonna go automatic on everything before we go manual. We're gonna get right straight to the section of the label. That's everything you can have. You can fold these. I have fold them in. Take some drop off, press where you are. Okay, so get straight to. Come on down. This is for station 4. We're going to go right straight to a section where you can do something with a voltmeter. And what I'm skipping, you can do next time or on your own time, which is a repeat anyway. Let's just go right straight to right here. So it's having you to measure voltage with 2 different sensors. With the inductive sensor and the capacitive sensor, I'm gonna pull up the schematic that we're using, and then you'll see what we're gonna be doing here. So go to station 4. Down here at the bottom, it says shaft 204. So that's the first page. Second page. Third page. The fourth page has the inductive and the capacitive proximity sensors. Those are the 2 sensors we're going to be looking at. So I'm going to go up here and then zoom in. So here's the points that you'll measure with your meter. That symbol, this symbol with the coil on it, that's an inductive sensor that picks up metals only. This is a capacitive proximity sensor that picks up metals and plastics. And it says here, metallic shaft detection, and this here just says shaft presence detection. it doesn't distinguish because this one can pick up plastics and metal. A capacitive sensor, that's a really big one, the round one, it can pick up metal and plastic. This one can. This one here can only pick up metal. It says metallic. So the way it distinguishes between what's really there is it judges it off of two sensors. So when you're going to check an input for the inductive sensor, you're going to check at the J113 and then go to common. If you check the capacitive type, you'll go from the J14 and then common. And common's going to be over here. So your common point would be up here. It'd be the X326. See that? That's all it is. So you can get those points there. X326 for common. And then when you come over, the state of the sensors will be there. Right now, everybody should come up and measure these two and record the information in the table. And you can fill in two of your blanks on your lab sheet right here. So for this would be for the inductive sensor. This is for the capacitive. This is missing in here. It should say inductive sensor, capacitive sensor. You don't have the paper? Yeah, my thing doesn't have the word. Does yours say inductive on it or not? I don't think it does. I actually put them in there. Well, I can't. No, it isn't because I printed off the computer. You doesn't say inductive. You didn't say that. You just add like this. Just put the word inductive sensor at the top. You can add the word inductive sensor up here where that says capacitive. This is for the inductive sensor. INDUCTIVE, inductive. And so right now for this one, there's plastic. So look, you're going to fill in this one right here for plastic on the inductive sensor. It's got plastic in front of it now. It's going to be 0, but you need to measure that. This one here's got metal in front of it, and it's going to be 24 volts, but you need to see it with a meter. Make sure that I want to see you be able to go to the terminal strip and do it. So the gloves and everything's over there already. So whoever wants to go first can come, do the two measurements, and then step back and let somebody else do it. You can sign it through that way, or whatever. We got about 10 minutes or so, or yeah. Right here. There's a measure right there. I'm just going to get my schematic.
I'll bet you would.
Don't work in pairs that time. Once you buy it, don't do it. Make sure you see what's going on. Next time you organize, whoever's on the team, you call them like that. When I put the brothers in, you can work in pairs for the most part. You work in teams. You have to work in pairs. Yeah, this just make sure, this is just making sure that you know how to get to it and find something.
Right little thing. 8 months. Morning, Lowe's. Oh, we're going. I paid for the battery. Yeah, I paid for the battery. I paid for a battery. And I get the day on. That's the thing about yeah. If my kids stop playing it, my kids found out that my book bag to go in my office sometimes. So last week I was trying to get my kids. Wait, no, so I had to get the tractor. I'm coming, I'm trying. Where we at? I don't know where. I say, where's the people tractor?
Man, that's right. I'll tell you what, I'm on my way back. Wow, you don't say that, Tom.
You got yours right on if you don't sit there, now you've got No, you put it on the first section. You put it on the first section. Put it on the first section. I know you're gonna say something smart. Look, I told you you should have never went over there and wired my dad on Western yesterday. Hey, Dad. You should never jump in front of me. Put the 0 on the first one. You see, look. He highlighted that one. So, I know I ain't done nothing since then. Today I ate lunch, remember? Sat there and ate lunch. So, yeah. Well, you were in the PLC with me, wasn't it? Intro PLC online, yeah. That was the one sitting in the car at Hodgeslack, remember? Because I didn't have no internet. Well, I had internet at the house, but it didn't have enough pool to pull the Zoom. So I had to go to business class to be able to pull the Zoom. But by the end of the semester, I was at the house. Remember? Yeah. Yeah, towards the end, it got easy after that. Jamie was in that class too, but he graduated last semester. Yeah. You talking about Victor? Victor. Yeah, he was in there too with us. Yeah. We're talking about the intro to PLC?
Yeah.
And we had to do it on Zoom, and I was sitting in the car, I had to do mine at Hawks Flat. I think we started off, what, 15 or 20 people we started off. Yeah. A lot of people dropped out of that class. Yeah. It was. Yeah, I wish we did too. Yeah, I wish we did too. Yeah. That is. I'm going to the house. We'll take some more pills.
Yeah, y'all have a good one. We'll see you Thursday. Well, slowly but surely, we're getting there. We're moving right on after. Yeah, well, you know, everybody's been busy. We'll get everybody's hands real busy. We'll index it over time. You got the passwords in there, you do definitely do that.
That's if I turn the power off, it just,
It stays for a while.
it stays for a while.
It takes the AC that comes in, it converts to DC, and then it puts on them capacitors, and they charge up real high. And then, whatever speed you ask for on that knob, you adjust that speed knob, it takes that DC off them capacitors, and it converts it back into the AC at a new speed, at whatever speed you ask for. If you look at something like that. If you run the pump a little faster, a little slower, it takes the DC and it makes a brand new AC out of it. I think they want to cut everything else off. Let's do it. Y'all doing good tonight. We're moving right along. We'll finish up with our schematics Thursday night. Multiple axis type machine like a robot or something that has more than one axis to it, they call it axis. Mm-hmm. Yeah. you don't normally call, if you just have a pump running, you don't call that pump an axis. You know. So there's no axis driver in this system at all. But I've actually ordered, I put a request to get some, but we just ain't, you know. It's $50,000 to get a 2-axis driver station to go in here that stores the parts whenever they come out the end. It puts them in a little warehouse. It's a 2-axis driver setup. It does a warehouse function, and that station costs $50,000. I think we'll get it at some point.
So did you say the frequency converter, you convert the 24 DC to it converts the voltage.
Well, it's the frequency converter. It takes the 120 that comes in to AC, it converts it to DC. And well, let's back up. The general purpose of the frequency converter. It's not asking you, oh, as far as power, it's got power and control. Well, this got 24 volt on it for one signal, but it's got AC going through it.
Yeah, so basically, you power it up with a 120, you convert that, and use the 24 volt to control a specific voltage to whatever you want to manipulate.
I'll show you right here.
But this is basically how fast does the shaft got to move, not the shaft, the cylinder has to move.
The cylinder coming down, yeah. Right here, that run signal is 24 volts DC. Coming from the PLC. The PLC is put 24 volts to protect the run. But you have 120 AC coming in. Coming in right there. And then leaving it, you got 330 volts. So that's you think you can get that high out of it, you can get a full speed with it, you'll push it back on. But this thing does two things. It converts single phase single phase 120 volt AC to 3-phase converter. And then also has a variable speed. Variable speed, so the knob right there. The knob lets you change the speed. That makes you make a point that fast or slow. The speed at that point on time. And I've got a point that's straight on that. So this also lets you have a variable speed point. It's a point with the speed.
When you say speed, one time, so it can make motion.
It'll come to the front more quickly. The motor will actually turn fast. I turn this here up, and the motor turns the front fast. It's the speed of the motor, make the front go slower. If you turn this down like that,
Normally, where I see this, the most is the vertical.
yeah.
Nowadays, sometimes, it's got like 4 3 or 4 whatever. I did the normally see the 120s, but I did it, see, we see it, or blood it, let it completely die out, and try to put it back in. So 0 voltage, and then slowly turn it back up.
Yeah.
Most of the time when that happens, I know it's like, like if you we start applying the ordinance, it's not moving, it's going up with voltage because the converter is probably jammed. Is it supposed to do that? This is another statement you can build since, that's my fault. Because the more we're gonna be pushing to, it's more sports. There's a little segment around here. One here. So I got that right there. The PLC stands 24, and that cable is going to be to start active money. So it's got a PLC behind it. You would use the link instead of letting the PLC run next to you. Like what I was saying. Like you know, you have to look at the time, you put it out there, and here it's going to go up and run. Because we have PLC on the wire and put it up here. The PLC does all that. Some of that see is the way that some of it, like small, especially small ones. All I see is that in here, and one of these. Sure, you don't have to have a PLC run that. Just think you just need a switch or a so they are this is continuously on. Yeah. This way continuously on. Yeah. They instead of up, it is have a switch. Yeah. Where people can actually outside. These are the other parts. You could the reason why the PLC does it when the PLC what's this part of that box in there? Then the PLC runs on, and we can turn on the dish, so the PLC does all the time. PLC basically is organized. It's organized. It's organized. Let me know when to run at what time. It runs the steps that the guy expanded. The guy expanded was succeed. It creates the program. If you want to do the instructions set, it's going in. If you can walk out and do it, you can walk out with the program. So we get text, you just walk in and find out how to build a laptop and see the program. You state that when you get the program, the first thing does that you actually get the program, speed program. Now, the question that I had was about this company, they wanted something out there. I think the name is ready, what is something? I think it's a local company. It's in the brand. That's all. Yeah, one of the companies how do it? Yeah, I mean, I remember the name was out of this, but I see a different name. It's changed. Huh? The name changed. The change was so it's the same company, just with a different name. Okay. Okay, that's what I wanted to find out. Because someone one time tried to get young with it, but really long time ago. They were also like $11 down. I would get $13 in restricted. So it's kind of surprising to see the Japanese company from famous now. The $24. If you want the boys to fit, start to $4. That's what it's saying. I mean, it's out here. I think you got one of these guys. Let's go. I have to look at it and see. I haven't seen that. And depending on, they say depending on experience as well, but I don't know, probably we gonna let them go in.
So that's catch right there. They're gonna look, if they gonna pay, you start out making that kind of money, 24, you gotta have a lot of experience.
In the paper, they make it look like it's really difficult to get in there.
Yeah.
Cause they say you gotta have a minimum of 3 years of automation,
Mhm. Yeah.
knowledge.
Mhm.
Of motor drive.
Yep. That's what the motor drive down there.
Basically, just one class.
Yep.
So they make it really difficult. I mean, it starts with the paper chase.
The best thing you can do is learn, focus on school right now. And you're working with the carpenter thing, the cabinet making.
Yeah.
Just relax and do it. You know what I mean? Do your job, enjoy your job. Whoever's watching, I'm ending now. So have a good evening. Have a blessed